Hey, what's up, guys? Yeah, so welcome to my analytic number theory video. So in this video, I want to go back and talk about for there are infinite primes of proof, and I will present four elementary ways. So I will prove that there are infinite primes by four elementary ways, and each way will give you different ideas of how the number theory working and various perspectives. Hope you guys subscribe to my channel. Okay. So we know that there are infinite primes, right? So the first prime is P1, P2 is 3, and P3 is 5. Okay, and in the analytic number theory, and you can prove that you can use, there are various proof. A common idea is that using the Merton's proof, so summation 1 over P is basically log x, okay? Or this is the Merton's theorem. But we are another theorem is famous called the PNT, prime number theorem. So pi of x is approximately 1 plus small 1 of x divided by log x. Okay, so this is the advanced idea to just definitely it's very easy to show there are infinite primes. But we are not gonna using this. We are gonna go back to the high school and try to use or the actually elementary school to show this proof. Okay, so method 1. Okay, so the method 1 is the I think go back to the 500 BC, basically the OCD the proof. So idea is that so proof by contradiction, right? So suppose there are finite primes. Suppose there are finite primes. So there are finite prime numbers. Then let's say this is P1, P2, up to Pn. Then you can define a large number P, which is P1 up to Pn plus 1. And obviously that this P do not divide this, every Pi do not divide P, because if you divide P, then the remainder is 1. Okay, so which proves that the P is another prime. Okay, so contradiction. So this proof is so beautiful that no one can beat it. It's so amazing. Okay, so the method 2. So method 2 is also the high school idea, but basically using the idea of the Fermat numbers. Okay, so the idea is that we do the same thing, right? We define let's define let's say f of 0 is 3, and I define f of n to be f of zeros up to f of n minus 1 plus 2. Okay, so notice that if you plug the definition, your f1 will be 5, because 3 plus 2, your f2 will be 3 plus 5 plus 2, which is 17, and you can check your f3 will be 3 times 5 times 17 plus 2. I don't know what it is. I remember it's maybe something like this. But is it? I mean I don't know. But you can try to compute this, right? Let me see. Let me just quickly compute. Oh, sorry, I'm stupid. Yeah, so 257. Okay, so this is the Fermat number. Okay, so you can prove by induction. So by induction, you can prove that this f of n just exactly 2 to the 2n plus 1. So for example, when n equals 0, you get 3. When n equals to 1, you get 3. Sorry, this when n equals to 0, you get 3. When n equals to 1, you get 5, and n equals to 2, you get 17, and then keep going. Okay, so this is proved by induction. Okay, so notice that fn is odd. Okay, so that means 2 do not divide fn. Okay, and obviously from this definition, then you can easily see this. You can easily see that fi and fj are coprime. If let's say j is greater than I. Okay, this is simple, right? Because your definition is let's say your fj will be f0s times some f of I here, and with some is ij plus minus 1 plus 2. Okay, so there are no possible way there is a other price, because the price the price of both gi and gj must be odd. right? So suppose let's say P is a prime which divides Fi and Fj, then you can just map P, then you get 0 equals to 0 plus 2, which map P, but P is odd, right? So this is a contradiction. Okay, so what you got is that Fn, Fj, J are coprime. Okay, so notice, so for different J and J different from I, so which prove what? There are infinite primes. There are infinite primes. Okay, the reason is very simple, right? Because they are coprime to each other. So if you keep generating the Fermat number, this Fermat number always contain infinite primes. Because Fn can keep increasing, then there's a pair of its primes, so there are infinite primes. Okay, so this idea is exactly the same as the previous idea, but the key idea is that in this case that one can actually write down the expression for this f of a. Okay, so let's introduce the method 3. So method 3 is also very old. I think it's probably not so old, but go back to Euler. So we use the idea of a zeta function. Okay, so I mean, I guess everyone knows about this so famous results. This zeta s, this is this definition works for the real s greater than 1. Okay, you can prove this by this is a definition of zeta function. And the zeta function has the beautiful Euler product, so which is belongs to the product of primes at least. Okay, so we got this, and we can just prove by contradiction, right? Suppose there are finite primes. Okay, and then you can, let's say you take s approach to 1, then the left hand side will be infinity. Okay, so this is due to your simple calculus, right? Because you can just prove this by using this is infinity, using the interval test. And the left hand side, suppose there are finite primes, right? So so this will be finite. Okay, because when s goes to infinity, this should be the infinite product. But if it's finite primes, there are finite products. So finite will become infinite, which is a contradiction. Okay, so this is third idea. Okay, so the method 4, which is a very appreciate of this idea, which is so smart. So this is the Erdős proof of their infinite primes. So amazing that so Erdős is a very genius guy that he come up with some idea that I guarantee that if I spend all my life, then I cannot come up with this idea. Okay, the Erdős proof is so amazing that so the idea is that this is somebody take you n, right? So let's say you choose n, let's say n is very large. So you pick the number, you pick an integer which is very large, and then you can easily, and obviously that for any n, this kind of number can be written as the r squared times s, where s is a square free. Okay, and R may contains the prime factors. R can contains the multiple, may contains the repeated prime factors. For example, you can write 12, right, equals to 2 squared times 3, right? So this is a square free. There's no square number, right? So for example, 60, you can write 4 times 3 times 5, right? This there's no duplicated prime factors here. So this is a square free. So square free means that there is no prime factor, no repeated prime factors. So basically, you can write n in terms of r squared p1. Let's say maybe up to like p something, right? So let's denote pi of n. Okay, so this pi of n is a number of prime factors, the number of primes which is less than n. So pi of n will be just a summation of 1 p if p is a prime less than equal to n. Okay, so this is the standard. This is this is the possible. Sorry, I should say this n can be written as r squared times the distinct prime factors. Let's say p1 up to pk, but k is less or equal to pi of n, because you may not use all of it. Okay. So what is the possible combination that one can get? So notice that these are can at most. So first notice that are at most. Let's see. R at most be what? Square root of n, right? R at most square root of n. So there, the number of possible values that the R can choose is square root of n. Okay. Okay, so maybe let's just see this. Let's say this is x, which is your x is less or equal to n, and you want to find all possible choice for R and P1 up to Pk such that it generates all this, right? So R at most is square root of n, right? So R have a square root of n choice, and the k, right? K has at most go to pi of n. Okay, so all the possible the number of possible ways to the right hand side will be square root of n times 2 to the pi to n, because for each there are all at most pi of n prime factors less than n, right? So you can choose or not to choose, right? And all these combination by default is less or equal to n. Sorry, it's greater or equal to n, right? Because each number less than n can be written as these kind of forms, and there will maybe repeated factors here, right? So this is a greater or equal to n. Okay, but which tell you what? Did you tell you that 2 to the pi n is greater or equal to square root of n, which pi of n is greater or equal to a half log n. Okay, so if you take n to be infinity, then the number of prime factors must go to infinity. The amazing thing is that this type of proof actually give you the weird lower bound for the number of primes. Right, so this is a very beautiful proof that so amazing that just using the combinatorics. And there are some kind of proof which you can prove using probabilities. Some probability idea that you can also prove their infinite primes. But I think these 4 ideas are very elementary. Hope you guys. Okay. So next video, I want to talk about the Burton's. I think the Burton's postulate. So this is the very non-trivial fact. So next video I will prove that there is a prime for let's say you take n greater or equal to 2, there is a prime such that p less than 2n greater than n. So for each you pick any integers, positive integer greater or equal to 2, there always a prime which falls into n and 2n. Okay, so this is a very deep, not so deep, but still very interesting. That you can prove this by by the way, this theorem also show that there are infinite primes. But this theorem can be proved by not using additive number theory, but using the very elementary mathematics. See you guys next videos.